precipitation gases and air atmospheric quantities. So I really like your title. So Lidar Wonderland, right?
Yes, that's the question.
Yeah. Please welcome.
Hello, everyone. Also, all the people online that I cannot see, unfortunately. So I will talk about my journey in the Lidar Wonderland with a special focus on wind energy applications. So this is some of our old vans. We were driving around in Europe making wind measurements here in France with some exotic palm trees. So I can go forward with some of this. Nederpilen. Here is a general introduction to myself, reflecting what you presented before. I have been quite some years working with LiDARs, and before that I even worked some years inside the small scattering materials, measuring gases inside them. It could be like fruits or different kind of materials. And the successors of me, when I had finished my PhD, built some applications for human medical diagnostics. And at the wind energy department at the DTU nowadays, I have been since 18 years about, and I'm mainly an experimentalist. So I give some different flavors of what I've been doing during these years as I have been working with LiDARs. So actually, I will go back to last time I was visiting China. And it's now 21 years ago, so you can try to recognize myself. It's probably quite easy. You can see a comparison here. I'm here. And this is my PhD supervisor, Sune Swarmberg. He's, I think, quite world famous in laser-based spectroscopy. He has been doing a lot of application of laser-based measurements of various things. So here we visited Harbin at that time. We have some colleagues and friends there that also spent some time in where I did my PhD work in Sweden. Yeah. Yes, let's go on. Here you can see an additional picture from this time.
Yes.
At that time, I worked with differential absorption. Tilted and rotated so you can scan out in the atmosphere. And in this case, we had a big project about mercury measurements. So in this case, we are placed next to an Italian chloralkali industry using mercury as one of the cathodes or electrodes in the process. And that has now, I think this year is the final year for China to, according to the agreements, to stop using mercury as an electrode in this process. But I think in Europe it has been banned for some time now. But that was a big thing with measurements of this. So what we do in the differential absorption LiDAR is that we use two different wavelengths, very closely spaced. I don't know if you can point. You can see this also online, that we send out something off this absorption line that has some kind of attenuation as a function of distance. And if there is something that particularly absorbs at this wavelength, you can see more absorption and decay of that. So this is the general principle of the differential absorption LiDAR that we use more than several close line wavelengths and take an absorption peak. So you can see then the ratio here as it decreases. You're moving some. Is it me or you?
Yes.
Yeah.
According to your party.
Exactly. You point here. We can see there's an illustration of these concentration plumes. You can then remotely deduct the concentration of this gas in this basically, the cross section of it. And by doing that, then you can produce like maps of the concentrations. So here is in the vertical plane in this case. And if you then know the the speed of the flow perpendicular to this plane, we can estimate the flux of these pollutants from the industry. And by that, we can basically measure remotely what is emitted on in this case. And here is an example of one of those factories in the old days. It's in the Polish one, and you can see like it's mercury around in the floor and so on. So that you can get some mercury. This is just some old pictures from this time. You can also see that is quite some time ago now. Nowadays we don't use this kind of if there is a young audience, you maybe have even not seen the fixed screens. That's where the standard way of doing things back in the time. So it's a LiDAR bus filled with optics. It's a neodymium pumped optical parametric oscillator that can then be doubled up and mixed, so you can come down to this UV wavelength used for mercury measurement at that time. But at that time, I mentioned for estimating the fluxes, we were very experts in measuring the concentrations, but we were not so much experts in measuring the wind. So we had some simple wind measurements very close to the roof of this building. But then after my PhD, I went on to DTU, where I have been working with LiDARs for wind, coherent Doppler LiDARs. And one of the first things I were involved in was this musketeer experiment. We think like it looks like this classical book about the three musketeers. They are crossing their three swords in one point, like we are crossing the laser beams. And by that, we can measure all three wind components in one point. So we get rid of this very big averaging volume you get from profiling LiDAR in that sense, but by directing all to the same point. But still, of course, having some averaging volume along the beams. And you can see from back in this time, some of the LiDAR musketeers. Yes, we had some European companies back in the time it was connected, but nowadays it's ZX LiDARs. So one of the chief technologists, Mike Harris, and the same from the Leosware. Nowadays the Weissweiler. If you are into business, you will recognize Jean-Pierre Carriot. That were part of these experiments, and we did it both with pulse system, wind tube in that sense, and then continuous wave system. This comparison. Yeah, you can read. I have put some references under most of the slides. You can read more about this kind of activities there. Yeah, so this is kind of from the European perspective, some of the pioneers in commercial LiDAR applications of these three companies: ZX LiDARs, Leosware, and Photonics. That's now by Lund. Yes, and at DTU, I worked a lot with this wind scanner, we could call it. I think Jakob mentioned it, that we have two different kinds of that. This is the pulse system, where you can measure over longer distances. And the thing with those is that they have a system that makes them possible to synchronize. So you can measure in the same pattern simultaneously. Also on shorter range with continuous wave system, we have also developed that. With at that time, like 15 years ago, we developed the scanning heads that is now used. I will come back more to the details of the continuous wave system, and the pulse system. We can just mention it is the classical with two mirrors that can be turned around. But let's go into this. Yeah, so this is a flavor of different scales. We can measure very locally with small telescopes. We have this continuous wave system that can measure a little longer away, and then going further out using pulse systems. And with different applications. I will go through some of those applications here now in the next slides. And as I mentioned, this steering of the beam is done by sending a light. You have the light coming up here through a prism that can be rotated. So you can rotate it around in a circle like that. And then it deviates once more. and then that prism can be turned, so you can reach all kind of directions within a cone that's plus minus 60 degrees. It's a quite heavy mechanical instrument for the scanning. And as Jakob mentioned in the previous presentation, as an answer to one of the questions that you could do this very rapidly, these rapid scans up and down. So you can basically do this 10 times per second. We studied a cliff here, a small island, where we studied the inflow. So we can study it at different heights, up to maybe 7 meters above the ground here at different incoming distances, and then we can see how the velocity, we have the velocity on the x-axis, and the height, how that develops together also with the turbulence, how that develops when you come in over land. So it could be like a scaled experiment for a very big cliff where you potentially put some wind turbines. So this was in order to understand and model this kind of recirculation zones behind the cliff. So I will change. We do further other applications. The thing that we used to do for several years was to investigate the downflow downdraft under helicopters. This is a rescue helicopter you can see up here in this corner. And then an important aspect, of course, if you're rescuing someone, is that you should not blow them away by the downward from the helicopter. So we used different configurations. Here we have used 2 of these continuous wave scanning lidars. You can see one over here and one behind here, scanning in a vertical plane between the 2 of them. We keep the laser beams inside that plane. That means that we don't get any contamination from the side. So then we can measure the vertical flow here. You see the flow under the helicopter, how it goes out on the sides. So that's good. That's an application of this continuous wave short range wind scan. If we more think about the wind energy, here's another example where we use pre-synchronized wind scanners, scanning in front of a turbine, a small turbine here in this case, scanning in a horizontal plane in front of it, and then we can see how the wind develops when you approach, going down here, approaching the turbine at different sideways locations. And what you can find out is that you can see this induction zone where the wind, the more close it comes to the wind turbine, it drops off due to the induction from the turbine. You can study these different components like this. Yeah, so if you're interested in particular things, you can just refer to this references here. And this is almost like a collection of strange, peculiar turbines now. Here is a vertical axis turbine that we studied in a similar way. We had to write some measurements here in a horizontal plane also, that then could be compared to different models, so I can use it for validating or checking their models if they make sense. And this is also illustrating, of course, it's always, when you present it, very, very easy to do the measurement, just put them up and place them, but there could be in reality some limitations. Maybe the optimum position of one of those lidars would be somewhere else. But in this case, we had actually some small lake here, and on the other side we had a railway, when they need optical fibers in between. So that's practical implementations that there are always some kind of limits that we should be aware of. And if we continue in this collection of very strange turbines, for some years we had a test turbine here with 4 rotors on the same power, and we can do the same here, scanning the vertical plane behind it at different distances, half a rotor diameter downstream, 1D, 2D, and then compare it to various kind of models. And we can also, I can talk a little about, of course, there was one question about how can you have very, very fast measurements and very detailed spatial measurements. often that can be tricky to have at the same time. So here can be an illustration of that. We can basically make a very simple cross or bow tie pattern here in 1 second, the whole pattern, to follow the fast dynamics of the weight behind the turbine. But then, of course, you don't get all these spatial details that you then can get if you instead make a very detailed scan pattern. You can do a scan pattern like this up here. That takes a minute, but it's very detailed. And then you can follow all the 3 components of the wind behind the wind turbine. And you can not only, you have the color here illustrating the actual wind speed. You can see the wake clearly, but you can also see the cross components illustrated by this arrow, how it swirls around behind the turbine. And another application is, of course, this coherence of the turbulence. That's important for all kinds of structures. In this case, we studied on a bridge. It's, of course, important to know if the wind you just measuring 1 point also hits the other points of the bridge in a coherent way, so it can start some kind of vibrations of the bridge, for instance. So in this case, we place 2 lidars on top of the bridge, and then we can scan here along a line, along the bridge deck, so to say. And you can follow in time how the wind fluctuates. You can see there is some correlation, a quite high correlation between the winds at different locations. Of course, with a small tilt because the wind were not totally perpendicular to the bridge, but had an angle to it, so it reaches some part of the bridge before our part. And from that, then you can calculate how coherent the wind is, increase the separation between the points. It relates to what Jakob talked about in this experiment that we do with the pulse lidar. It had recently been doing now on the west coast of Denmark, studying this kind of coherence over several hundreds of meters, up 200 meters, and as Jakob mentioned before. Yeah. So that's some ongoing things to try to understand how that can be used to be able with the modeling of. And then we will have some analogy about the continuous wave system. Probably you think about lidars as something that average the wind speed over quite big volumes. But it's similar to when you take photos. I'm taking 3 photos of a small model wind turbine on my desktop in front of my screen background. And you can notice some difference between these three images. Hopefully also online, if it's clear enough everywhere. I think here in the room we can clearly see that the left image is quite blurred in the background, but the one to the right is quite, it's also blurred, but not so blurred on the tree. You can see it's a tree at least. In all of them, you can see a sharp turbine. So the difference between them is, of course, the opening size of the lens. So we have different F numbers, like correspond then in this case with maybe 50 millimeter focal length of this kind of opening diameter. So it means that the bigger opening you have, the more shallow depth of the field you have. So you only see things very close to where you focus the beam. And that's the same thing when you are measuring wind. If you can focus very tightly, you reduce your measurement volume. And that, you can illustrate it by this here. And that can typically be illustrated by this kind of weighting function as a function of distance, where you focus it. If it's a certain distance away, this focusing point, it goes down like this. You have a Rayleigh range. This is actually a half width of the half of the full width half maximum, half width half maximum. It's described by the Rayleigh range. It depends on the range to the distance from the lidar to where you measure, and also the opening size of your telescope. And from that, you can then understand that by making a bigger telescope, you can reduce the sampling volume at a given distance. So that we have done. We have most of the first measurements I showed were done with a 3-inch size optics. I wonder how it looks this camera actually. Can you see if they see me or? I just noticed that sometimes I'm behind.
Camera.
There is a head in between us.
我们能看见视频吗 ？This camera is not open.
Just Riso.
No, only share screen.
Yeah.
Okay, only share screen, yes. But they don't see me even. Yeah, so you need to point. Yeah. Yeah. Okay. I thought it was over there, but yes. So we have this quite big one. This is 6-inch optics, and that means that we can reduce the damping volume. And if you look at this Rayleigh range again, we can also understand by reducing the distance to the measurement point, you reduce the measurement volume. It goes actually down quadratically with the distance. So if you just take 1/10 of the distance, then it means that it goes down to 1/100th of that length. So that means that if you're doing measurements at maybe 10 meters distance, then the size of this volume is about a decimeter. So it's in the order of the size of a classical. So you need to point here. Yeah, you have where you see the red lines are crossing, you have a sonic anemometer. And if you look very carefully here, we have placed the 3 components of the measurements. Of the wind measurements, and actually there are 2 red lines and 2 blue lines and 2 green lines. One from the Lidar retrieval and one from the sonic. Then so they are almost following each other, and this is not average over several days. You can notice that the timeline here is just 6 seconds from left to right, so you can really follow the high fluctuations, high frequency fluctuation of wind. And we have used that then to do this. Oh, maybe is it there? Here. Yeah, I think Jakob showed one of those. I showed another. I showed a vertical speed under a small drone that we measured up here. You have the drone up here. We have 3 crossing lidars that can then be scanned in a plane under this drone to study how the flow is, and the purpose was actually to put an anemometer on this drone. I think tomorrow, but maybe not for online, as Tim will talk a lot about the details about this comparison between what we have to the left here, the CFD simulations, and the measurements with the lidar. And that can be done because of this very small volume of the measurement with the LiDAR, if it's a continuous wave LiDAR and you're focusing on just 10 meters distance or even shorter.
Now your video is on.
I'm also online.
Yeah.
Hello, everyone. Yeah, so maybe you can see when I point on the screen directly then, if you would like to do that. Yeah. So let's go to the next slide. And I'll do that. Yeah, so it's the same. So let's take a tour to Milano from Denmark. We went down to the wind tunnel there with this kind of wind scanner. You can see it here. And we talked about alignment. Jakob mentioned how important it is to align the beams when you're outdoors, and if you're offshore, you need a drone. But on this scale, it's even more precise alignment in that sense, because now we are thinking about yes. You can see here a car that actually lights up, so you can see the beams, and you need to have very careful alignment, because the things we are studying is, in this case, I will come to that, small model turbines that is just less than a meter in diameter. Yeah, here is an example of what you can do with these two wind scanners. In this case, you can see them in the left figure here, the 2 white things here. Scanning in the big wind tunnel that is 13 meters wide and 30 meters long, I think, and 4 meters high. And you can see all these roughness elements on the ground, and also in the inlet to the tunnel to create some boundary layer here. And what you can then see is a vertical measurement here of the wind field on the actual component of the wind. And you can see kind of how the fluctuations kind of varies together with this inlet structures here. And the purpose in this experiment was actually to study a wind farm, small wind farm, 3 wind turbines, how you can steer the waves by how that could be used to sort of optimize the whole wind farm energy output. Here you see a measurement of these 3 waves when they are aligned with each other almost. Yes, and the wind direction is of course very fixed in a wind tunnel. So what we have to do here is that we have placed the wind turbines on a big rotating plate that could be rotated to illustrate different incoming wind directions. And another time we went down with some even smaller telescopes. In this case, we have 2 telescopes. You can see in the end of the red lines, it's outside of the screen here, but up here you have 1 telescope where they were on the big structure that can be moved around, and then they have a crossing point. And in this case, we had a model. I showed before this coherence measurement on a big bridge that actually is a bridge in Norway. And here in the wind tunnel, we have a model, a scale model of that. And then we can measure the wind speed both with this LiDAR and compare it with some pressure-based Cobra probe measurements. So you have up here the actual dew component well above the bridge. So it's not really affected by the bridge. And then you can compare it, and if you go down here to how it looks like, you get much more turbulent activities in the wake behind the turbine. And you can see that this Cobra probe, that's like a point measurement, is comparing quite well with the LiDAR results. At least for the actual component here, you have some variations on the vertical component that we see to the right in the wake and above wake. Yeah, so this creates some opportunities to use measurements without introducing too much distortion due to the point measurements. And it also requires less alignment and less backscattering than other optical techniques, typically like PIDs and laser Doppler anemometry in wind tunnels. Another such short-range application had been in a wave tank in France. Here we see some measurements of that. And I think I included this to illustrate the importance of, if you're working with LiDARs, to store the raw data, the Doppler LiDAR data. Because if you have a Doppler spectrum here, and the location of the peak tells you what is the wind speed. And if the spectrum looks like this, then your algorithm might pick up this around 0 here. But in a wind tunnel, you can pick up vibrations from all the walls that are quite close to your measurement location. So in this case, if you had done nothing, you would see kind of 0 everywhere. But if you treat it in a better way, then you actually detect the flow. You can see in the previous slot we have this pan. So this is a scan of half of that flow field. So this is an important aspect. Not just to save the end result, but if you save the raw data, you can always go back and check. So if you don't do that, you could fail most of the measurements you're doing if you're in a more complex situation than you normally can expect. Yes, we have also tried this in our wind tunnel. We saw this very fancy big picture in Jakob's presentation of the big fan of that local wind tunnel we have at the DTU. And it's very heavy. Actually, it uses maximum 2.4 megawatt energy power to run this fan. So it produces a lot of heat, and that needs to be cooled down. And that has some drawback. You can see here is a cross section. It's basically, it's made for testing blades of wind turbines, at high speeds, so they can measure up to 105, or we can produce up to 105 meter per second wind. And it's also an acoustic wind tunnel where they can shift the normal walls into some Kevlar mesh that lets the sound through, and they can measure the sound outside of the wind tunnel. But the drawback here, this is just an illustration. If you send some, we saw a nice here in this city yesterday. We can see the light scattering through the atmosphere here due to some kind of particles, and it's the same if you go to various kind of arenas. They add often some kind of smoke in order to make the light visible, the light beams. But that's a problem in such a wind tunnel where you are cooling down the air. There is no water vapor, and all the particles are then less giving less backscattering. So we have problems to get very good signals. But we can solve that by adding some smoke. Yeah, you have here in the purple, yes, the signal strength from the general background. And if you do nothing, then you have, it can be very difficult to differentiate between noise and the real wind speed. But by adding some kind of smoke, you can it can be possible to measure. But the problem is in this wind tunnel, we don't like to have too much of this smoke. So it has been an issue to actually get some signals when you're really having a very real clean environment. Yeah, so this very local measurement actually started with what we call the blade lidar. We did some measurement back in the days on a turbine blade by placing the telescopes out on the blade. And that was in connection with the first spinel lidar measurement. We have heard some, maybe, I don't know, did you mentioned some of the spinel lidar, maybe not. But we have one of the now expert on analyzing this data way, or here today. And the name is called spinel lidar because it was placed in the spinner of a turbine. So there should be no obstruction from blades behind, in front of the lidar. So we did this in order to actually scan the whole inflow, not just one point. Here's an illustration. I think in the early days, the rotor were quite small compared to the height of the turbine, which is not the case today. This is still a small turbine, so it's even more different ranges today, where you even reach very high up over the boundary layer. That is a current topic for a lot of studies to understand how the turbine is affected by this by being so very high compared to the boundary layer. And so for doing that, we developed something based on this mechanism of two prisms that can rotate. And in this case, it's a simplified one that rotates with a fixed speed with a particular gear ratio that makes this scan pattern, like a rosette, that is taking measurements from a lot of different points. And by doing that, then you can see the whole inflow. For instance, if you're having a wake coming into towards the turbine, if you would have just a few beams, maybe you're getting some wrong conclusions. By having the full field of the wind, you can get a better idea about what's going on. And recently also we have applied this lidar that we call the spinel lidar also behind the blades. And for that we developed some way of filtering out the blade returns by just modeling how the blades are rotating. That gives a radial wind signal that depends on your the sidewise component on your pointing vector and the displacements above the center of the rotor, and the same for the vertical part of it. This is just a simplified result of it. You can read more about it this down here. And this support spinal LiDAR can also be used in other scenarios, like we did together with some people in the US, where they placed it looking backwards to study the weight of one turbine at different downwind distances from the turbine. Yes, now we are almost at the end. So currently we are running an European Marie Curie training network for PhD students. We call it APTWIN. And at this meeting here, we have from a previous such Marie Curie training network, actually three persons that completed their PhD are now also here today. Like we have Jim, Wei, and Fung. Yeah. Yes. So there will come a lot of new PhD students in a few years. We have been ongoing now for 2 years, but it's maybe a little more than 1 year for most of the PhD students. We have 15 PhD students distributed in these orange countries in Europe, working with a lot of various atmospheric flow modeling, but also with LiDAR applications. We have some projects together with European LiDAR manufacturers. You can see Lumibird here, DC2, and we have also Vaisala, the DC, for instance. And then a lot of turbine manufacturers and different industries using wind turbines, like the developers of wind farms and owners of wind farms, and also some small companies doing various kind of calculations of wind and turbine. Yes, so thank you for your attention. Yeah.
This Laoshan,
This is from last time I was in China, 21 years. This is in Beijing.
Oh, in Beijing.
Yes. Actually, they are. I think they are providing me one of these red books of Mao. Yeah.
Okay, thank you very much.
Yes.
Very nice wonderland. It's a great journey. I think you slide as a very powerful tools to study for us. Yeah, so many things, including turbine aerodynamics, so many things. So okay, we do have we have 2 questions online, and yeah, please raise your questions. We are opening time for questions. Let's see. So first, the question about do you adopt the LiDAR? Okay. Oh, I don't think this question is for Mikael. I think this question is for Jakob, maybe.
Comes in.
Maybe. I just repeat the question to say, do you adopt the LiDAR? Double equipment cost may reduce vector error by only 0.2 meter per second in TI, turbulence intensity larger than 12%. What's quantitatively metric? Use a second scanner, or say like a 50 megawatt rotor, and at what top height separation distance does this marginal improvement fall below 5%? Wow, that's I think it's a very specific question. How to use dual Doppler LiDAR to reduce the error, right? So what's the marginal improvement? So do you have any comment on that?
But it depends on where you do the measurements, and if you already have a wind turbine and you have some profiling LiDAR close to the turbine, then I think you could make some mistakes. That you have some beams inside the wake, some outside of the wake. So I think it would be very difficult to do these kind of wake studies, for instance. Profiling LiDAR.
Yes, I agree.
But if you have a flat terrain, then I think it's nice.
Yeah.
Then doesn't improve too much. Maybe Jakob.
Do you have any comment on that, Jakob?
Well, it also depends on what you want to measure. If it's
Exactly.
a mean wind or if it's a turbulence.
Yeah.
It's very different.
Yeah. Yes, I think so. So two professors just depend on the case.
Yes.
It measures the mean wind or the turbulence. Also, I think for the turbulence or non-homogeneous wind, the measurements is not adequate anyway. So, okay. So the next questions.
Require some investigation for a
Yeah.
particular case. It's about.
Okay. The second question I think is for the data availability due to the low aerosol or icing case. So the question said this low aerosol or icing will cause let's say 10 to 15% in data loss or data gaps during winter nights. So do you have any physics informed feeding technology? I think it's used neural networks. So for example, she mentioned proper orthogonal decomposition and the Navier-Stokes informed again. I think this generative adverse network, something like that, this machine learning technology can improve the spectral or the coherent structures. Let's say improves the data availability to 90, how to say this, or so that it's very complex question.
It's a long one here.
So the 99 percentile extreme lows extrapolation changes by less than 2% compared to the completed record. I don't understand correctly.
I guess basically the question is about how, if you're doing a more long-term study, then maybe there is some influence from that you're not measuring it during some cases where you have maybe very low backscatter.
Yeah. I do read a few papers about that. DRR, some colleagues published use neural networks and machine learning technology to like extrapolation or make a guess of data we lost due to the low errors.
Yeah, that could be relevant.
Did you have any?
I haven't applied it myself.
Okay. Interesting.
That is an interesting question.
Okay. Anyone else? Any questions or maybe in this room? Yeah, please.
So what is the difference between China, where you visited last, now?
Good question.
It was two different places here. So that was Harbin and also Beijing.
Harbin, I think Guangzhou as well. It's a Mercury Lidar in Lund University. The Professor Swanberg.
Yeah, he has been to some other universities.
Yeah, I think so.
He left, yeah.
I think Huanan Normal University or something.
Yeah, exactly,
Yeah. Very interesting.
But I was only
This picture reminds me a lot of memories.
But it has been a huge development of all the LiDAR activities here in China.
Yes.
It's very impressive factories we have seen here.
Yes. Thank you. I do have a measurement about the helicopter's downdraft.
Yeah.
So it measures the winds, use a scanning LiDAR or use scanning the three wind scanner to coordinate the scan each part of the wind.
Exactly. Yeah, this is this coordinated short range continuous wave scanner.
Okay. So how long do you need to measure this whole volume of this field?
Yeah, I think it was very challenging situations, of course, because you have all kind of speeds here. So it's an average speed over a longer time. Yeah. I don't remember now, 10 minutes at least.
Oh, yeah, minutes like that.
Yeah.
Okay, thank you.
Because of course it fluctuates a lot, and you have all kind of speeds in your measurement locations.
Yes. Thank you. And I can update. Ms. Jiang just sent me a message about the audience. Now it's 15,000 people online.
Okay.
Oh, another question about Nassau Mountain LiDAR. May provide 8-second prevail, but streamwise coherence drops to 0.3 at 1.2 D diameter for stable conditions. Oh, this is the expert on wind turbines. So which frequency-dependent coherence model do you use in the feed-forward controller to avoid introducing 2 or 3% additional DLE. I don't know what is DLE. Oh, DLE. Okay. On the shelf, and what field data prove the trade-off is robust across stability classes. Yeah, I don't know. Maybe they can
Yeah, it sounds like a question for David Schlipp, but he's not here right now. Or maybe Wei can answer that.
Yeah.
It's also into the turbine controller.
Maybe you can check this question. We are expert on it.
Maybe this question refers to that he found some additional loads using feed-forward feed control. So I think this question depends a lot on how you tune the feedback controller. So maybe it's just because if you have the feed-forward controller, your feedback controller can be much more relaxed because you know what will be the future wind speed. So you have to just try to retune your feedback controller, make it less aggressive, and maybe you won't see this negative reduction, a negative increased loads, because we have done a lot of investigations. Usually for the shaft related loads, it's with LiDAR will definitely be helpful with feed-forward control. So that may be something worth quite.
Okay, thank you. Hope the audience here's the answer. So very good.
Yeah, we provide an email address here if you have some additional questions.
Yes,
you're
for sure.
welcome to.
Yeah, for the audience online, you can check the email of Mikael and also Jakobman. And if you have any questions, can contact us. Okay. 如果大家有问题的话，可以线上联系这个我们的邮箱，然后包括未来海洋学院，我们也有邮箱可以联系。刚才回答问题的是上海交通大学的郭峰博士啊，还有就是现在在德国 Svanto 的这个傅伟博士，他们2位呢都是上回说到这个玛丽居里项目在欧洲的项目当中的这个我们3位都在这儿是吧？我们现在还有3位，还有金立奇博士都在这儿。他们都是用激光雷达或者用这个遥感技术去帮助风电，所以这个希望能够回答你们的问题，好吧 ？Okay, so we're close to the 6th. Okay, thanks again, Mikael. Thank you for wanting to
Thank you. Thank you.
是可以就线上就可以关掉了，不知道可以开的问题。好，非常感谢这个姜老师，非常感谢您。Thank you, Miss Jiang.
哦，谢谢吴老师，谢谢。